Many proxy measures depend on chemical isotopes. Changes in the relative amount of various isotopes for a given element provide an estimate of temperature, atmospheric carbon dioxide concentration, age, photosynthetic activity, and oceanic pH. Some educators believe that the topic of isotopes is way too difficult for you, our viewing audience. I argue that if given the appropriate information, you will gladly transcend from being an isodope to being an isopope. Please don't prove me wrong. An atom is the basic unit of matter. It consists of a dense central nucleus surrounded by a cloud of negatively charged electrons. The atomic nucleus contains a mix of positively charged protons and electrically neutral neutrons.
Although no one has yet found a way of getting a close-up view of an atom, different experiments have made it possible to build up a picture or model of what atoms consist of. The colours in these models are of course used simply to distinguish between different particles. In the centre of an atom is a nucleus. This is made up of even smaller or subatomic particles called protons and neutrons. The protons each carry a positive electrical charge. The neutrons are as heavy as protons but carry no charge. This means that overall the nucleus is positively charged, and orbiting around it are negatively charged particles called electrons. The size of the negative charge carried by an electron is equal to the positive charge carried by a proton. Now the electrons are moving at incredible speed, in fact 3/4 of the speed of light, so what stops them shooting off in any direction? If we could pull an atom apart into its components, we'd see that a neutral atom has the same number of electrons as protons, and it's the force of attraction between the positive and negative charges that prevents the electrons escaping. Each type of atom is identified by the number of protons and electrons it has. A hydrogen atom has just one proton and one electron. An oxygen atom has 8 protons and 8 electrons. An iron atom has 26 protons and 26 electrons.
Each chemical element has a unique number of protons in the nucleus of an atom. For example, a carbon atom, C, has 6 protons. Usually a nucleus will have equal numbers of protons and neutrons, but not always. The number before an elemental abbreviation signifies the sum of protons and neutrons. The common form of carbon is carbon-12, which has 6 protons and 6 neutrons. Carbon has 14 other isotopes ranging from carbon-8 to carbon-22. They have from 2 to 16 neutrons respectively. The most common isotopes, carbon-12 and carbon-13, are stable unless subjected to nuclear bombardment and comprise about 98.9% and 1.1% of all carbon respectively. Many isotopes are unstable and decay at a predictable rate, emitting a radioactive particle and becoming a different element. The unstable carbon isotope, carbon-14, as mentioned in the previous segment, is produced during a nuclear bomb explosion. This isotope also is produced when cosmic rays strike the atmosphere. It accounts for 0.0000000000001% of all carbon on Earth. The half-life of carbon-14 is 5,730 years. That is, half of the carbon-14 atoms present at any one time will decay within 5,730 years. When carbon-14 decays, it emits a beta particle and transforms into a stable isotope of nitrogen, nitrogen-14. The other radioisotopes of carbon are much more transient. Their half-lives range from 20 minutes for carbon-11 to less than a billionth of a nanosecond for carbon-8.